Hi everyone, welcome back to Production ML Papers to Know. In this series, we'll give you an overview of the most important papers to know if you're building machine learning powered products, from the classics to the new and promising. And this week, we're going to cover an exciting recent paper that shows promising results in a problem setting that's becoming more and more relevant in production machine learning today. So let's dive in. One of the biggest things that's fueled the success of deep learning over the last 10 years has been an increase in the amount of data that's been available, starting all the way back with ImageNet. And it just turns out that deep learning scales really, really well as you add more data. But datasets like ImageNet require human labels, which often ends up setting an upper bound on the amount of data you can realistically collect in these datasets. Human labels are just expensive. So to move past this, in the past couple of years, the trend has been to train on massive amounts of data scraped from the web, and to set up scraping so that you can get labels, or at least noisy ones, as part of the scraping process. For example, in GPT-3 or Copilot, these are self-supervised models, meaning you use the training data itself as a source of labels. And that's the problem setting this paper studies. We're training on tons of labeled data, with lots of GPUs running in parallel. And we do actually have labels for these data points. So it's worth noting that this is a different problem setting than one you may have already studied, which is active learning. Active learning and data selection both study the setting where we have more data than we know how to use it, but active learning is harder because we assume we don't have labels and we have to pick which data points we're going to acquire labels for. So coming back to data selection, naively, the way that we would approach this is to sample. As we run stochastic gradient descent, we'd randomly sample each batch from our whole corpus until we run out of our compute budget. The goal of this paper is to study whether we can use our training budget more efficiently than that. So whether we can reach the same loss with less training data, or whether we can reach a better loss overall for a fixed training budget. That brings us to the first key idea in this paper, which is online batch selection. Let's say that we have 1 billion data points and we train our model on a mini batch of just 128. Normally what we do is we'd shuffle the data set and sample 128 at a time. But in online batch selection, we first sample, let's say, 10,000 data points from the 1 billion, and then we rank them according to a label-aware selection function. The key question here is, what is the right selection function to use? That brings us to the first baseline of this paper, which is just selecting data points that have a high loss. The obvious thing to try for this selection function would just be to use the loss function of your model itself. And the intuition here is that data points that have high loss are ones that might be better to train on than random ones, because ones with lower loss are already learned and they can be safely ignored. So we can think of this as avoiding redundant data points. In other words, finding data points that are not yet learned. However, this also selects for a couple of types of data points which maybe are undesirable in our training process. For example, some data points in the training set may be noisy, so they might have a wrong label, for example. And we don't want to train on those because they're not learnable. Other data points might be outliers. They'll have a high loss, but they aren't important for our model performing well in the real world because we just won't see many data points like this. So these data points are not worth learning. And that brings us to the second key idea in this paper, which is the row loss. Here's how row loss is defined. Let's talk about what this notation means and how it helps us address the issues that we identify with the baseline. Let's start by ignoring the part after the minus sign and just focus on the left-hand side. In this notation, dt is the training set up until the point in the training process that we're at now, before we sample this batch. What this term means is the loss of the model trained on dt on a given point xy, or in other words, the loss of the model we're currently training on the data point we're currently looking at. So if we take the argmax over all of these loss terms, that's saying, show me the points in the batch with the highest training loss. And that's just the baseline that we looked at before. Now shifting our attention to the part on the right, what this notation means is, let's calculate the same loss function L on the same point xy, but for a different model. Instead, it's a model trained not on our training set, but on a holdout set dho. The way this works is that before we even start training our main model, we train a smaller, less accurate model called the irreducible loss model on a subset of our validation set. We hold that model fixed as we train the bigger model, and just use it for computing the row loss throughout training. That's it. So putting this together, the row loss tells us to select points from our batch where the loss of the model that we're currently training is high relative to the loss of that irreducible model that we trained before. So let's talk about how this addresses the issues. Just like in our baseline, if a data point has already been learned, then the training loss on the left-hand side will be low, so this number will be small overall. Now, let's say that the data point has high training loss, but only because the label is noisy. In other words, it's a data point that is not learnable. In that case, since the label is incorrect, the irreducible loss model won't be able to predict it either. So the term after the minus sign will be large as well, and these two will cancel each other out. So this data point won't be selected by this algorithm. And finally, let's say that the training loss is high on this data point, but only because it's an outlier. In other words, it's a data point that's not worth learning. It's not similar to anything else in our data set, so it won't help us in the future. In that case, the training loss will be high, but the irreducible loss will also be high since the outlier wouldn't be present in the data it was trained on. So the two terms, again, will cancel each other out and the data point won't be selected. So in summary, the way that this algorithm works is before you start, you train a small irreducible loss model using a smaller model that's going to be less accurate and trained on a smaller holdout data set. And then for each training iteration, you sample some data points from your corpus, you rank them according to this row loss function, and you take the top points according to that function and you train on them. So that's how the algorithm works. Now let's talk about, does it actually work in practice? Here's the main results of the paper, sort of the key chart that they showed. And this is training a range of different models on this clothing 1M dataset, which is a dataset of 1 million data points that are scraped from the web. And the x-axis here shows training steps and the y shows how accurate the model is. The top line is the row loss technique and the bottom line is the baseline. They show an 18x speed up over the baseline, which is really, really good. So obviously very exciting. Let's dig a little bit deeper. I think the other really promising finding is that you really don't need a huge model for the irreducible loss model. So the x-axis on this chart shows how many fewer epochs of training you need with the row loss relative to the baseline to get the same level of accuracy. Points on this chart further to the right are better because they're more sped up. And the color of the dots are the data set that we're looking at. And each row here looks at a different problem setup. In the first row, they use a big model for the row loss. And in the others, they use a small, cheap ConvNet. This shows that you don't need a big holdout model to use this technique, which is exciting because it means it might actually be computationally efficient to do this. A few other conclusions from the experiments. They ran experiments on a number of other data sets, and they found that this technique still works on clean data, but it's really most effective when your data is noisy, like when you have data points that have wrong labels or the labels are a little bit off. It also works for NLP. And another really interesting finding is that this irreducible loss model that you trained before you start training the model that you're studying can be reused. It can be reused by other practitioners working on the same problem. It can be reused for different hyperparameters, different model architectures that you're studying. In principle, at least, just a cost that you have to pay once before you start experimenting on this data set. My takeaway is that if you're working in the problem setting that this paper studies, then it's worth paying attention. The pros of this paper are it's really simple to implement, which in my experience is telltale sign of techniques that are going to stand the test of time is that they're easy to implement. And there's strong results on the experiments that they do run. Now, it's worth noting that there's a few parts about this paper that maybe make it less applicable. The first that's worth noting is that the experiments that they run don't actually match the scale that they are talking about where this is going to be useful. The million images in the marquee data set that they studied are much, much smaller than web scale experiments that companies are actually running these days. It's worth asking whether these will actually scale up to a scale where this is really useful. Second con is that you need labels. So that means that this doesn't apply to every problem that you might work on. A third con, and this is, I think, a little bit more speculative, but one of the benefits of this technique is that it helps you ignore outliers. So don't feed outliers back into your training process. But I'm actually not really sure whether that's the right idea in practice, because a lot of times in practice, we really care about outliers. Those might represent edge cases where you don't have a lot of data yet, but it's still important for your model to be able to perform well on the data that you do have. Lastly, this does add computational overhead. In order for this to be useful, you need to have a lot of scale already, and you need to also implement a bunch of other tricks that make this more computationally efficient and make the trade worth it. That's it for this week. Join us next week to learn about more exciting production ML papers.